In this lecture, I am going to teach you the next phase of combined stress, that is biaxial stress. So first of all, what is in by biaxial stress means, in the system, the stress is acting on both x and y direction. Okay, so that is called biaxial stress. So to study the principle of biaxial stresses, we must recall the principal stress first. Okay, so first let me tell you what is meant by principal stress. At any point in a strained material, there are three planes mutually perpendicular to each other. So these planes will carry only the direct stresses alone. So there will be no shear stress. So these planes are called as principal plane, and the stress acting at these planes is known as principal stress. Okay, so we have two directions, sigma x and sigma y. So the principal stress sigma 1, that is the maximum principal stress, is of sigma x minus sigma y plus root of sigma x minus sigma y the whole square plus 4 tau square. So here this sigma x and sigma y are the normal stress acting on the plane, and this tau is the shear stress acting. So similarly, at an angle 45 degree from the principal plane, the maximum shear stress will be acting, and the maximum shear stress can be calculated by using this equation. Tau max is equal to of root of sigma x minus sigma y the whole square plus 4 tau square. So this is the equation to calculate the maximum and minimum principal stress, and this is the equation to calculate the maximum shear stress. So the purpose of this principal stress we have used in the combined stress equation. Now coming back to the combined stress equation, in the second case, that is axial plus torsion, the resultant stress can be calculated by using the principal stress equation. Okay, so if you substitute plus, then you will get the maximum principal stress. If you substitute minus, then you will get the minimum principal stress. Okay, so here in this case too, we have used the sigma 1 or sigma 2 as the resultant stress. Okay, so here in this equation, I have replaced the sigma x with sigma a. So both are normal stress. So I have replaced the sigma x, that is your principal stress equation. So in this equation, I have replaced the sigma x with sigma a. There is no sigma y, that is there is no perpendicular stress is acting, so we can neglect the sigma y. So it is sigma a plus or minus root of sigma a square plus 4 tau square. Then this is the equation to calculate the maximum shear stress. So this maximum shear stress can be considered as the resultant shear stress in the case of axial plus torsion. Then in the case of bending plus torsion, the only difference is here bending stress will be acting. Since there is no axial stress, this sigma x is replaced by the sigma b, and here also there is no perpendicular stress is acting, so we can neglect the sigma y. Okay, so if you substitute plus here, then you will get the maximum principal stress. If you substitute minus, then you will get the minimum principal stress. So this maximum and minimum principal stress can be considered as resultant normal stress, and this is the equation for maximum shear stress, and this maximum shear stress can be considered as maximum shear stress. So if you have a problem on axial plus torsion or bending plus torsion, then you have to use this principal stress equation to find the maximum and minimum principal stress, that is your maximum and minimum resultant stress. Further, if you want maximum shear stress or maximum resultant shear stress, then you can use this equation to find the maximum shear stress. So now with this, we'll move into a simple problem. A shaft of 40 mm diameter is used to transmit power of 30 kilowatt at 710 rpm and is supported in bearings 500 mm apart. A load of 10 kilonewton is concentrated at the center of the shaft, acting vertically downward. Calculate the maximum principal stress and shear stress. Okay, so here we have to calculate the maximum principal stress, that is sigma 1, and the shear stress, that is tau max. So first, by looking into this diagram, you can see that a 10 kilonewton force is acting at the center of the beam. So this beam is actually a simply supported beam, because in the problem they have clearly mentioned that the shaft is supported in bearings 500 mm apart. So the shaft is a simply supported one, and this 10 kilonewton is acting at the center. Okay, so the first load is a bending load. Then coming to the problem, the shaft transmits a power of 30 kilowatt at 710 rpm. So you can see this 30 kilowatt power is transmitted at 710 rpm. So if a shaft is transmitting power, then twisting moment will be there. So if twisting moment is acting in a shaft, then definitely torsional shear stress will be there. Okay, so the first stress is bending and the second one is torsion. So this comes under bending plus torsion, that is case number 2. Okay, so first write the given data. The shaft diameter is 40 mm. The power is 30 kilowatt, so 30 into 10 power 3 watt. The speed is 710 rpm. Then the length of the shaft is 500 mm. Then the concentrated load acting at the center is 10 kilonewton, so it is 10 into 10 power 3 Newton. So we have to find the sigma 1 and tau max. Okay, so now we'll move into the problem. So first we have to consider the bending alone. Okay, consider the bending alone. We will calculate the bending stress first. We know that the bending stress for a circular cross section is sigma b is equal to 32 m divided by pi d cube. This is for a circular cross section. This we have already discussed in the previous classes. So in this equation, sigma b is the bending stress and m is the maximum bending moment. Then d is the diameter of the shaft. Okay, so as I told earlier, the shaft is a simply supported one and a point load is acting at the center. Okay, so for a beam with point load at the, for a simply supported beam with point load at the center, we know that the bending moment m is equal to WL by 4. So this is the maximum bending moment for a simply supported beam carrying a point load at the center. So m is equal to WL divided by 4. So we have already studied this formula in our strength of materials. So here W is the load acting, so I am going to substitute it. It is 10 into 10 power 3. So you can see the given data. W is 10 into 10 power 3 Newton. Then L is the length of the shaft. It is 500 mm divided by 4. So if you solve this, you will get 1250 into 10 power 3. So this is actually 10 power 3 Newton meter. The unit is very important. We have substituted the load in Newton and the length in mm. So we will get Newton mm. Okay, so we have calculated the bending moment m and we know the value for d, that is diameter. So we can substitute it. Sigma b is equal to 32 into 1250 into 10 power 3 divided by pi into 40 cube. So the diameter is 40 mm. So you will get 199 megapascal, that is 199 Newton per mm square. So we have calculated the bending stress. The next we'll move into the shear stress. So now consider the shear stress, that is tau is equal to 16T divided by pi d cube. This is the equation to find out the shear stress for a circular cross section. The T is the twisting moment and d is the diameter of the shaft. So to calculate the d, in the problem they have given the power and the speed, and we know that P is equal to 2 pi nt divided by 60. If you substitute P in watt, then you will get T in Newton meter. So I am going to substitute everything. So T is equal to P into 60, bring the 60 to the left side, divided by 2 pi n. So P is 30 into 10 power 3 into 60 divided by 2 pi. The speed is 710 rpm. So we will get T is equal to 403.5 Newton meter. So to convert this Newton meter into Newton mm, I am going to multiply into 10 power 3. Okay, so 403.5 into 10 power 3 Newton mm. So we'll substitute this in the first equation. It is 16 into, in the place of t, it is 403.5 into 10 power 3 divided by pi into 40 cube. Since the diameter is 40, it is 40 cube. So we will get 32.1 Newton per mm square, that is 32.1 megapascal. Okay, so we have calculated the shear stress. Now we have to combine both the bending and shear stress. So sigma 1 is equal to 1 by 2 sigma b plus or minus root of sigma b square plus 4 tau square. So we have calculated the value of sigma b and tau. Now you can substitute everything in this equation. Okay, so remember that to find sigma 1, here you have to use plus. Okay, so if I put plus, then the final solution will be sigma 1 is equal to 204 Newton per mm square, that is 204 megapascal. And the maximum shear stress is 1 by 2 root of sigma b square, this is sigma b square plus 4 tau square. Okay, so substitute the value of sigma b, it is 199 and tau is 32.1. So if you solve this equation, finally you will get tau max is equal to 104.5 Newton per mm square, that is megapascal. Okay, so about this problem, first we have to calculate the individual stresses, that is bending and torsion. Finally, we have to use the combined stress equation to calculate the maximum principal stress and maximum shear stress.